Okay, we're good to go.
Okay, fine. So just a moment. I will just share my screen, and you can just confirm to me that it's running all right.
Yes, yes.
Mm, Okay. Do you see this?
No.
No, just a moment. Yes. Now.
Yeah, there it is. Yeah,
Oh,
it's fine.
fantastic, fantastic, fantastic. Okay, so I will just come out of this for a moment and stop sharing screen. Then we'll come back to it once we're starting. So we are ready to start, Ken? We have people
Yes, we are. Yes,
here
we are.
already. Okay, fine.
Yes.
So hi everyone. Good evening, and thank you so much for coming out on a Saturday evening. I think I'm looking forward to this possibly more than you are. It's always very nice to get back to college, speak to some of you, and thank you so much, IE. Thank you for everyone who reached out to me for making this conversation possible. So they call it Samwad, which is conversation, and that is really good. That is what we require now, because in today's world, which is increasingly connected, you need to stay connected. You need to keep having conversations, dialogues, not just with the people who are around you, but with the more people from different times, different fields, different specializations, because that is just how we are moving. We are no longer at a time when we would work in a certain silo, in a certain field, and we didn't need to interact with others. That's not how it is now at all. So the more you interact with different people, the better it was going to be in the long run. Uh, and yes, as the host has mentioned, I would invite all of you to keep leaving questions, comments during the talk. So we'll address them all at the end. And if there is something that would be better addressed in between, then I will do that as well. Because as you said, it's a conversation. So we'll try to keep it a little interactive in the sense that you can keep letting me know what parts you would like me to focus on more and less, so we can do that, right? And just one last thing, some of the things which I will be sharing now are from certain sources, so I would request you not to screenshot, not to print screen. I'm leaving my email ID here. If you want any information about any of these things, if you want any of these images or anything, I will send it to you with a proper source, but please don't screenshot it at the moment. All right, so let's start. um, yeah. Are you seeing this full screen now? Can someone please confirm?
No, it's not full screen yet. We
It's
don't
not full
see it.
screen. All right, all right, all right.
No.
Yeah, now.
No, not yet.
uh, okay.
I think maybe stop sharing your screen, make it
And then
full
start
screen,
it
then
again.
try
Yeah.
to do it again.
All right,
Yeah.
that might be good. Mhm. Let's just do it once again. Yes. Any luck now? Hello.
No,
Uh,
it's still the same. It's still the same. Well, it's
so
not
what are you
changing.
seeing now? You're just seeing me, or are you seeing the presentation slightly also?
I see the presentation, but it's not a full screen.
Yeah, it's not a full screen. All right. Um, Sorry, folks. Just give us a moment while we set this out. Okay, what I will then do is I'll just make it a little large over here so that
Yeah, I
maybe
can just zoom
it'll
in.
be
Yeah.
similar to a full screen share, right? Yeah, does this work? Okay, just one last time. Yeah, any luck now? Is it full screen?
Uh,
No,
I,
still
I,
not
I don't
proceeding.
see your I don't see your screen at all.
Oh, then okay. Right. Share screen. Share screen.
Mm. Do you want to send it to me and then I can present it for you? Maybe that will work.
Yeah, that also is fine.
Uh,
You can
I guess
please
this is
WhatsApp
fine.
me. Yeah, it's fine. Okay, fine. Then let's go with this.
I think it works.
Yeah, okay, fine, great. Right. So before we start on that, okay, Nisha, so a few of you are here. Fine, it's okay. You can see the screen clearly. That's fine. We'll work with that. It would be nice if you could, those of you who are online, could just drop down which branch and which year you're from, so that as we proceed, we will try to cater more towards what you may like a bit, right? So you could please start putting down those details in the chat, and then as we go along, we'll try to take those into account. Anyway, so in the present moment, we will start from here. So uh, we had quite a lot of samvad with the IE team before this started, and it went through a lot of iterations before we finalized on this topic. So the initial idea was to talk a little bit about materials and metallurgy, how metallurgy is related to other branches, how metallurgists have to work with other engineers, how other engineers need to work with metallurgists. Because as I was saying earlier, once you leave college, once you leave NITK, and once you enter any industry, this is presuming you are working in a core industry, in a core job, your branch, what you've studied really doesn't matter. All that matters is how you can work along with others to make something possible, right? To bring something into reality, something that is abstract or something that's in thought into reality. And for that, you need to be open to working with multidisciplinary world. And the great thing about NITK is that you do have that opportunity multiple times. You have so many branches, more than most colleges have. You have a lot of interactions. One of the modes is clubs like IE, and even otherwise, I think now you have a much more relaxed system where you can take courses from other departments and so on. That's a great move. So just keep that in mind, and keep in mind also that that is a great advantage that you have already being in NIT. So this was what we initially thought of going with, but a lot of your IE colleagues had said that there is some apprehension that some of you have with regard to career opportunities, with regard to placements, with regard to jobs in these fields. So I thought it would be good to talk a little bit about those as well. So we will be doing that also. We'll try to mix the two in a way that it is that everything comes together, right? And if at all at any point something seems too abstract
Ashran,
or
sorry.
yeah,
Can I
yeah,
can you
please,
just
please
send
tell
me
me.
this PPT so I can try to present it? Do you
Okay,
while
fantastic.
you're talking?
Yeah, yeah,
Let me
yeah,
just
sure,
give
sure.
it a shot.
Yeah, yeah. You could just send me your ID via WhatsApp or something.
Yeah, I will. Just 1 minute. Just let me send it to you.
Okay. So in the meantime, right. So I see one chat, third year metallurgy. That is nice. I am also from metallurgy, and okay, maybe in the meantime, I will just tell you a little bit about how my journey started off after college. So I graduated in 2013. I was doing my BTech in metallurgical and materials engineering. That time we did not have the major and minor system, so I was completely in metallurgy. And then I joined in 2013 itself the Department of Atomic Energy. So I started off in Bombay in the Bhabha Atomic Research Center, which is better known as BRC. I underwent training over there for a year. I will be talking about that program a little later, towards the end of the talk, maybe. And this training is like a 1 year intensive classroom come laboratory training. So it also serves as MTech, as the first year of MTech. So it's a unique opportunity where you can get to study along with work. And then after I finished that 1 year of training, I was posted to another unit called the Indira Gandhi Centre for Atomic Research. This is in a town called Kalpakkam. Kalpakkam is in Tamil Nadu. It's very similar to Surathkal on the opposite coast. So just like Surathkal is between Mangalore and Udupi, Manipal, we are between Chennai and Pondicherry. So it is a small town, coastal small hamlet, a very beautiful place, just like Suratkal is. So thanks to NIT, I feel very much at home over here. And over here, I work in the area. I work in the metallurgy group. I work in the area of metal forming. That's where I specialize. So that deals with essentially shaping metals or metallic materials, alloys into shapes that are useful or that are required. This involves a lot of high temperature work. So that is where a lot of my experimental work goes. And alongside, I have for the last 2 years, I've also been pursuing my PhD at ISC Bangalore. So it's been a lot of different institutes and a lot of different groups that I've been associated with, and through all them all, I'm completely unambiguous, and I'm very sure that NIT was the best time that I had. And what NIT has given is what has prepared me to a large extent for everything that comes. So, if you ever feel that uh, things are tough, that the job market is down, just remember that just by being over there, you're already ahead of the curve. There are a lot of people who don't have either the knowledge or the prestige of the institution that you come from. So just keep in mind that even if things don't seem very good, they are better for you than they are for a lot of people. Just 1 minute. I will. So what I'm doing now is I'm just mailing you the presentation, so probably you can share
Yeah,
from
yeah.
your end
Yes,
while
yes.
I okay, okay, fine. So I've sent it to you whenever you're ready. Kaushal, Ken, you could
Yes,
start
yes.
sharing that. Okay, right. So I was talking about a bit of uh, how things started off for me. And well, I was sure that I wanted to work to pursue a profession in metallurgy. So things were quite simple for me back then. Like my route that I wanted to take for career was pretty well known. For a lot of people, it was a very confusing time, and I see that things are not changed much. I've been told that there's still a lot of apprehension and things, so we will be getting to that at the end. But before that, to do justice to the title of this talk, we will talk about materials, how they are important, and most importantly, what I'm trying to stress is there's no way I can replace or compete with what you're already learning in class. So this is more along the lines of what you should keep in mind when you eventually go on into a profession and try to practice it in the area of core engineering, that is wherever you are. And as you will see that there are really no actual concrete boundaries in the professional space in terms of your discipline or in terms of your former education. So always keep that in mind. And probably at the end, we'll also talk a little bit about the COVID situation and how that might be affecting things, because I suppose that is also on your mind, especially the ones who are about to graduate, and some tips on what you can do to deal with that then. Right. So, meantime, in the chat, I have only got one person's discipline, so that is metallurgy. So see, the thing is, if I only get metallurgy people, then I'll dwell more on the metallurgy parts, and all you non-meta people may be a little bored. So that's why I want to have some idea of the demographics here.
Aashranth, I still
So
haven't received
yes,
it. Did you? I still haven't
okay,
got the email.
you haven't. Just a
Uh,
moment. Just a moment.
Let me just write another email ID. Maybe that will work.
like seem to be running into a little bit of my system hanging over here.
That's okay. That's okay. We're
Yeah,
good.
yeah, it will just happen.
Yeah, guys. So I think there's a small problem with his laptop, so he'll be joining in shortly. While he tries to figure out. Guys, can you see the screen? You just let me know if you can see the screen. So he can join back. Okay, great. Okay, he's just joining with another laptop, so he'll just get back here soon. Oh, fuck. Hi, Aashranth, can you see my screen?
Yes. I can.
Hi,
Thank you.
can you see
So
the screen?
yeah, I can see it. I can see it. So you will operate it, is it? I just tell you when to move on, and then you will do it. Is that how?
Yeah, that works. That works. That works.
Okay, very sorry, friends. I'm sorry for all this technical uh, glitch. Mostly at my end, my laptop just hung, so I logged on to a different one. But this is Murphy's law. Whatever can go wrong will go wrong. So in the meantime, thank you so much for putting down all your branches and your disciplines. So we have lots of mechanical, electronics, electrical, computer science, IT. Wow, that's nice. Met a few people. Fantastic. All right. So before we get into the main thing, could you go to the next slide, please?
Yeah.
Right. So this is a bit of nostalgia for me. So I was a very proud member of IE and ITK back at the time, and this is just a few images to show you how things started. So in 2009, the all we knew about IE came from these bulletins that were printed on a printer and put stuck up on a hostel walls. That is the first image on the left hand side. So that time the IE ran a newspaper called Synergy, which was interesting enough to make a lot of us join. And in 2011, a group of people started doing a lot of robotics, automobile related stuff. So over there, what they have is they made a small maze, and you have a small remote controlled bot, and you got to maneuver it through different obstacles. So that was like an event that was there for different things. And as all these things started gathering steam, the idea to come up with special interest groups came up. And the thing at the bottom, the screenshot at the bottom, talks about Garage, which I'm so glad is still continuing the same name. And this was the time when we were just starting off, 2012. So we were looking for things that we could do in Garage, looking for places where we could get some funding, projects that we could do, ways we could attract people, participate in some inter-college events and things like that. So it had a heavy focus towards automobile, little bit of aerospace, but essentially mechanical engineering applications. And look today where we've come. Right. So this is in the time when we used to use Google Groups as the primary group communication. This is in the pre-WhatsApp days, and look at how far you've come now with all your website, with so many great things, and with events like Samwad, which is filling such a big gap in these times of COVID. So congratulations to all the IE members, and there's so much more that you're going to do, and we're all very proud of you. So let's go ahead a little more. And yes, I can tell you from my personal experience that I did not join the metallurgy branch because I wanted to. In After my class 12, that was essentially what I was getting, and that's what I got. And that is the opinion which most people have. I'm sure those of you who are in metallurgy, most of you probably also wanted to study physics or mechanical engineering or something, and then this is what you got, and you came here. And it so happens that metallurgy tends to be a little bit of a thought of as a marginalized branch because it's not there in many colleges. In fact, if I'm not wrong, in Karnataka to date, this is the only undergraduate program. Probably there are two of them now, one in Bangalore and one there. So it is a very niche thing. But despite all that, materials do matter. And the next slide, please. Yes, and they've always mattered. So we'll just go through a bit of that. All right. So this is like story time, nothing technical. Just sit back and enjoy this. Yeah, next slide, please. Okay, so you think about where the early Homo sapiens were, a long time ago, millions of years ago, and where we are now. And you see, interestingly, the rate of change that has happened. So if you were to think of it as a function, you're looking at now the derivative of the function. How fast have we moved from the early Homo sapiens to primitive agriculture? It's a long time. From there to weaponry and organized industry has been a lot shorter time. And from the industrial revolution to our present day, when we have modern technology, we're going to space, we are recreating the thing, we're splitting the atom, so many different things, right? And that's just happened in 300 years. So what is happening to make technology grow at increasingly faster rates? We are evolving, that is fine. But how is it accelerating? Right. And next slide, please. And the answer, as some of you may have guessed, is to do with materials. Because it's not like our anatomy or our intelligence has really grown greatly in this period. Essentially, the early Homo sapiens had the same amount of intelligence. If you could measure his IQ, be the same as ours. So what has changed has really been the way we experienced materials around us and the way we started using them, right? So in the initial Stone Age, uh, we used stone tools. Then as we started using metal tools, we got some ability to handle shape metals. Agriculture became possible in a mass setting. Then when we found copper and bronze, when we could start using them, then we could extend this a little more. But still, remember, at this point of time, we were still scattered in different bands or different tribes at different parts of the world. It was really the mass production of iron and steel which allowed us to make large groups of human civilization, which have now become countries and so on. So it was because there was so much iron that you could organize an industry, you could build an industry. Most importantly, you could transport material. So for a long time, it was the case that, if oil is found in a certain geography, that's where oil is used. If ice is in a certain place, that's where ice is used. And if minerals are in a certain place, the minerals are only used there, even if they are mined. So it was to a large extent, it was the discovery and the ways to produce and the ways to mass produce iron that led to industrialization. Of course, that led to colonialization. So the countries which developed this technology first went out and started conquering other countries alongside weaponry and industry. So weaponry and military, as you will soon find out, has been one of the biggest drivers of all growth in materials. Every major change, almost every major change, is somewhere linked to some military application that was developed for. And from then, the last 100 odd years, we understood how to use silicon, so that gave rise to all the computing, heavy metals, and radioactivity, which is leading all our nuclear energy efforts. Radioactivity is also giving us a big boost in medicine. So like in cancer treatment, we are also increasing our longevity. So we live longer than we've ever lived in the times. And in summary, you can say that every leap in the human civilization has been because of an advance in metallurgy of the times, right? So if you look at external factors other than the sociological factors, then technologically, this has been the one thing which has accelerated our growth every time. And even sociologically, it's because of these developments that we started living in groups. So there's a fantastic book called *Sapiens*. I suppose some of you have read it, and if you've not, I highly recommend that. This lockdown is a great time to spend time reading all this. So if you read that, you will realize that for a long time in our history, we were not the largest animal, we were not the most intelligent animal. So what led us to create this civilization and overpower all other species has largely been our ability to stay together in large groups and to command large groups. So technology has played a large part in that, because it's because of that we came together. Right? Could we go to the next slide, please? Right. So the question is, why should we use metals as tools in the first place? Right. Stone is much more easily found, much more easy to just pick up. It's easy to sharpen. Today you get metallic knives and things very readily in the market. But if you look at the technology that goes behind it, you need a proper industry. It's not something that generally you can just make at home. You need a smithy, you need a foundry, you need a forge. It takes a lot of things. And if you see, copper is actually, which you remember the Copper Age and the Bronze Age, copper is actually softer than a lot of stones. And yet, copper tools worked a lot better. You go next, please. Yeah, so this video will probably not play here, but essentially what is being done over here is this person creates a stone axe and, next please, and a copper axe, and tries to cut the same thing with them, right? And it cuts much faster with the copper axe than with the stone axe, even though the stone is harder. So when we think of tools, and essentially an axe is a tool, so what kind of material are we really looking at for a tool? So we know already it has to be hard, because that is what is going to cut through. But there are obviously some other things which is making copper a better tool than stone. So could we go ahead, please? Yes. So this is a key slide, and I like to think that it has something to do with how we deal with life also, right? So like I said, stones are harder than copper, so they are this thing. But there is something called toughness, okay? So there is something called strength, there is something called resilience. So strength just means how much of load you can take. Okay, these three are in normal language, they're used interchangeably. But toughness is different from resilience, and that is different from strength. So the stone down there, that is strong because you cannot deform it very easily. The stress ball that you have there is resilient because you deform it and then leave it and it comes back to its original shape, right? So it is not taking any damage. Toughness is the thing on top, the cartoon of a boxer being punched down and then coming back, right? So it's the ability to sustain damage, to take damage and be able to move on. And that, just like life, that is what is the key factor for using materials in all our applications. So it's not that they're the strongest things around. We have stronger materials than metals. It's not even that they don't take any damage, because they do, but they can take damage and still continue working. And if you were to look at it a little philosophically, that's how you got to be in life, right? You cannot be the strongest person around. There will always be situations which will overcome you. But what you need to work on is being able to bear that, being able to come back from that. So, okay, back to metals. So if you look at the graph in the middle of the screen, it has stress and strain on the X and Y axis, which I presume you've come across in school. But just essentially, stress is essentially the amount of load that you can impose on a certain cross section of a material, and strain is how much it deforms. Okay, so you have different combinations of things. You can have a material which is strong but not tough. So you'd like to use that in a place where it's going to take a lot of load but not much damage. You could have something that's very tough but not so strong. So something like our boxer cartoon, something which is going to take a lot of damage but doesn't need to be too strong. And you can also have something that is strong and tough. And you can vary between these three types of behaviors with very, very subtle modifications in the composition. By composition, we mean chemical composition. That's the elements that constitute a metal or an alloy. And processing, which is either mechanical, that is by loading it in certain fashions, or by thermal, which is heating it. We call it heat treatment, or through a combination of these three. And this is what makes metals unique, because these combinations, this versatility is not something that we find in any other class of material. All right, could we go next, please? Okay, and in the meantime, you can still keep leaving comments if you would like to, know anything more about this, or if this is too fundamental, if you would like to move on, you would like me to go faster, also you can keep mentioning that there. Okay, now we move to a bit of history, right? So this is once civilization has started, and we move from copper to bronze. Now, copper, as you know, is a single metal. It's a metal, and bronze is an alloy, right? It's an alloy of copper generally with tin. So you have at the bottom two bar charts. So these are two types of strength called yield strength and ultimate tensile strength. I assume mechanical engineers and metallurgical engineers are familiar, but for the others, all you need to know at this point is yield strength is the amount of load that it can take before it starts permanently deforming, so before it starts sustaining damage. And ultimate strength is the maximum amount of strength that it can take before it finally breaks or fails. So if you want a material which does not damage at all, then you need to stay below the yield strength. And in any case, you need to stay below the ultimate strength. So if you look at it, the bronze is higher in both these strengths than copper. And on the other side, processing. Processing is very important historically, because in historic times, before we had a lot of technology, we had to make do with the little bit that we had. So if you need to melt a material, metals are generally high melting, with the exception of certain low melting metals like mercury. But you see, copper is, compared to copper, bronze is a much lower melting material. So to prepare a fire or a flame that can melt it and process it, it's much, much easier to do it with bronze. So that is the reason why, from the processing point of view. And this is an important distinction even to keep in mind whenever you work in a practical setting. You may have, like on the left-hand side of the screen, we have certain properties that we really desire. On the right-hand side, you have how difficult it is to achieve those. Okay, so you may want certain properties. It may be possible to get them, but at the cost of achieving them, and cost is not just financial cost, but energy cost, material cost, specialization cost is too high, then probably you need to see whether you can make do with lesser qualities. And similarly, something may be very, very easy to process, but if that does not give you the properties that you have, then it's not going to be very useful for you. Okay, could we go to the next thing, please? All right, so this I will probably go through in a very short time, but I hope it will interest you anyhow. So this has to do with the previous thing. So when we move from a metal to an alloy, so an alloy is essentially a combination of two or more metals. Okay, so as soon as we mix two of them, in most cases, it creates some kind of defects within the material, and these defects are what make the material strong. And this is a very subtle point which is difficult, and I find this in practice because I work on multidisciplinary teams with physicists, mechanical engineers, chemical engineers, which people often find a little hard to grasp that it is defects which give material the unique properties. So a particular kind of defect which is called a dislocation, that's what makes materials the way they are. That may also makes them easy to deform, and it's by playing with the dislocations that we also make them strong. So in, again, a philosophical sense, it's like the weaknesses or the defects in you that can also be your greatest strength, right? Because perfection is very limited. When something is perfect, there's not much you can do to it. When there are imperfections, you can engineer them, you can tailor them to give you the properties that you like. And the same thing, this mixing of two metals is exactly why the smelting or the melting becomes easier for bronze compared to copper. And at this point, we'll just leave it at the fact that dislocations are what help you to deform materials. And as soon as you add a new kind of element, a new kind of atom into your material, that atom interacts with dislocations in a different way, in a more aggressive way, and that prevents them from moving. So that's why you get a higher strength. And because of this interaction, so this is a theme which again comes across everywhere. Whenever you have two unlike things interacting, there is always a certain amount of friction or energy between them. And that energy always creates either some sort of heat or some sort of extra stress that is created. If it's a single type of thing, just like with people, you have very like-minded people who get along very well. You add one person who thinks very differently, you start having some friction. But that's also what we are doing here to get to some beneficial properties. So just introduction of some new kinds of atoms changes your properties so much that you can start using it you can start processing it more easily. You can get better properties out of it also. Right. The next slide, please. Okay, and thank you for the questions. We will come to them. Very interesting questions. Thank you. Okay, so now we come to iron and carbon, and if to your friends in metallurgy, when you speak to them, they will tell you that is all they hear about in 3 years of metallurgy, probably 80% of what they hear, right? And when you think of it, steel is all around us, iron is all around us, and still we keep studying it. And this example will probably help you understand why there is so much of diversity, so much of versatility. Okay, so just like earlier we spoke about copper and bronze. So you added tin to copper to make bronze, and that gave it all those special properties. It lowered the melting point, it made it harder, stronger. Similar thing happens with carbon in steel, carbon in iron. So when you add carbon to iron in certain amounts, it forms steel. And just so you know, steel is not a single material. There are millions of steels today. Even stainless steel is not a single material. There are millions of stainless steels now. So steel is a broad class of materials which has predominantly iron and carbon. And nowadays we add a lot more things to it. But look at the three products at the bottom, the three images. So these are three wire-shaped products, right? So the first is a needle, like a sewing needle. So it's rigid, it does not bend. Then you have your orthodontic wires, your braces. Those are the same kind of needles. They bend and they retain their shape, right? So you can that's how you can use them to wear braces, because they mold themselves according to the shape of your jawline. And thirdly, you have a safety pin. You can bend it and it will come back to its shape, which is essential to its function, right? You need to bend it to open it and then close it back. So these three are all steels. They have very minor differences in their chemical composition. So it is just by playing with their properties a little bit that we can get such different properties. So the point of showing you this is that if you have an understanding of materials, you can make these very subtle changes and access a wide variety of technologies which would otherwise not be possible to you. Whereas imagine if we did not have iron and steel, we would need three different kinds of materials for these three different functions. And one thumb rule of industry is that if something can be mass produced, it's produced cheaper. So you'd always like a situation where you can produce one single material in 10 tons rather than having produced 10 tons of 10 or 1 ton of 10 different materials. So that leads to a lot of prominence that iron and steels have in our time. Could we go ahead, please? Right. So this is a little bit of background into why this happens, and I will just not get into this looking at the composition of our audience that we have here. But I will just leave you with this one thought that it's again an anomaly, which you could think of as a defect in this system, and that is why iron and steel have this particular property which no other element has. So this particular anomaly, which I will just leave you with the fact that it deals with magnetic structure of the material, the way materials become magnetic above certain temperatures, and below that they have a different kind of magnetism. So it's a very unique thing. There's probably only two elements in the entire periodic table which have this, and no other element has this, and this is what gives it all its unique factors. Otherwise, you may wonder, why did iron become the most widely used material? It's not that iron is the most commonly found material. Now, sure, we because we preferentially mine iron and we extract iron. So, incidentally, any mining engineers in the audience, so please leave it in the chat if you are. Right. So we now preferentially make iron, but the reason for forming it was because it has this inherent versatility. You can make so many different things with it, which is not possible with any other element. Right. So we will just go ahead a bit. The next slide, please. Probably we'll go 2-3 slides ahead. Yeah, one more slide. One more. Okay. So let's just leave it. Just one slide back, please. Oh, we'll just leave it at there is an anomaly which causes this behavior. But this is the science or the reason behind it, which we now know quite well, and we exploit it to engineer things. But the fact is that in a lot of, if you look at a lot of historical inventions, the technology has come first and the science has come later. And India is a very nice example for this, because our tribes in Jharkhand, this is known as the Asur tribe, so they had made small furnaces, right, with nothing but just pedals. So if you see the man, he's operating pedals just like you would cycle. And that is producing flames of a temperature high enough to melt iron. And iron and steel melt at very, very high temperatures, well above 1,300, 1,200, 1,400. That is the range in which iron melts and steels melt. So we've somehow figured out ways to do it. And this was the tribe which was producing iron tools, iron implements. Now, of course, and as civilizations advanced, they were overcome, and then the technology was taken, and for a long time it was dormant also. But even now, this production does happen in some of the tribal areas of Jharkhand and surrounding areas of Bihar as well. And you just look at the iron pillar, the Delhi iron pillar. I'm sure a lot of you have seen it. Most of you have definitely heard of it. So it is a unique pillar which has been around for really long. I'm sorry, I don't remember the date when it was constructed, but I think it was the Lodi dynasty. But it's made with a certain type of process, which we now know, which we now invented as solid state welding, which causes it to remain so corrosion resistant. So it's been there for so long. And in comparison, you just look at any gate, like you look at your hostel gate. Surathkal is on a coastal area, so there's a lot of saline, a lot of salt in the air, and that causes a lot of corrosion. So if you put an iron piece, it's not going to last for more than 7-8 months. And this is something which has been lasting hundreds of years. So we have had the technology and we've had unique ways to use it from time immemorial. And it's only much later that the science has come into play. And the lesson from this again is that sometimes while working with some of these things, you figure out that some particular solution works, and then you go back and find why it works. It doesn't always work the way it does in the textbooks, right? That you know the theory, you know the reasoning, and then you go and implement it. Sometimes the reverse process also happens. Okay, yeah, the next slide, please. Right, so this is again, this we call this diagram a phase diagram. It basically represents different phases. So phases are like states of matter. So you have solid, liquid, gas. In metallurgy, we like to divide the solids into a lot of different kinds of phases, and those are based on how they look under a microscope, how they're physically arranged. So I'll not get into the complexity of this, but just by changing the temperature, by changing how fast we heat a metal, how fast we cool a metal, we can produce a huge number of different microstructures. And microstructure is the way that the atoms are arranged, the morphology and the shapes in which things are arranged. We'll see some examples of how that affects properties. And all those little circles that you see, which have some diagrams inside them and which have some Greek alphabets inside them, those are all essentially different structures. So just without knowing anything, you can just look at this diagram and see that there's about 8 different structures that you can produce with iron and carbon alone. And this is just by changing the heat treatment, right? By changing the way you heat it, the way you cool it. And each of these 8 have very, very different properties. Could we go next? Yeah, fine. Finally, we come to some examples. So this is something which I think will resonate with a lot of you. So gears are something that all of you have seen. So what you're seeing on the left is just a cutout section of a gear. So, a gear has teeth, and the teeth are what mesh with each other and rotate and then transmit power. So gears are essentially devices or components which transmit power, right? So constantly, if you have 2 gears contacting each other, they're meshing. That means these edges or the teeth are constantly hitting each other. So that produces a kind of load on the material. And that can eventually lead to failure. So if you look at the red circles, you see that it is starting to break over there. And if you keep using this gear at this time, it's ultimately going to break down. And that is going to cause a lot of overheating in whatever machinery it's being used in. And I can tell you that the prime reason that a lot of components fail in industry is because of friction and overheating. So just like your fan in your room will creak if it's not oiled well, just like your bicycle chain needs to be oiled periodically, or whatever automobile has to undergo regular servicing, is mainly because these metals must not keep rubbing against each other without suitable lubrication, without some way to reduce the friction. And that is what is happening over here. So this big crack that you're seeing is now seen under a microscope at a very, very high magnification. So you can see that even in the microscope, there are small lines, which is inside the red oval. So those are cracks. So those are micro cracks, which initiate separately and they all join up and then they make this big crack. And just to give you an idea, the yellow bar at the bottom of that image on the right is about 20 microns, 20 micrometers. So you can see how small this is. And 20 micrometers is like 1 micro is 10 power minus 6 meters, or 1,000th of a millimeter. So it's much smaller than what you can see, of course. But there's tiny cracks like this which happen at such a small scale. And those come up and lead to such big failures. So that's why the title of this talk is From Microscopes to Mass Production, because you need to start solving the problem at that stage, right? When it's still very small. Stitch in time saves 9. That actually has a lot of bearing in practical metallurgy in all industry. So could we go next, please? Right. So this is, again, what we call microstructures, the way things are arranged. And I told you that steel is an alloy of iron and carbon. And as a rough estimate, the more carbon a material has, the stronger it is. Now, the way this carbon is arranged in the material can differ greatly depending on the heat treatment. So in the image on the left, this is again seen under a microscope. You take a piece of metal, polish it, you prepare it in a certain way, which metallurgists will tell you is the most boring thing that you do in college. And then you treat it with certain chemicals and it reveals the structure, it reveals what's inside it. So it's a very exciting thing when you get to doing it, but the process of preparing these samples is exhausting. So the white lines that you see, a web-like pattern that you see in this, is how the carbon is arranged. And for the metallurgists, this is cementite. This is a hyper-eutectoid steel, so it preferentially forms cementite. And this white phase, now we're coming to applications of a phase, this form of carbon is very brittle. And as you saw on the last slide, that those micro cracks, they propagate along some web-like pattern. So the way this carbon is arranged is the way it is going to start cracking and the way it is going to fail. So the moment you have a web-like pattern over here, this is a very, very brittle material, a different, an undesirable way of having the carbon. But what do? You need carbon because that's what's giving you the properties. So the solution is you heat treat it. And when you heat treat it, this is a special heat treatment which we call spheroidizing, which means making spheroids or spheres. So that all those lines, that web of white carbon, has now turned into tiny spherical balls of carbon, which are again dispersed all over the microstructure. Probably they're too small for you to really make them out, but on your screen, if you just see some small dots, those are what the carbon has gone into. And uh, this is a theme which occurs frequently in both mechanical engineering and in metallurgy, that whenever you have a long directional brittle part, a brittle component, that is likely to fail. And the moment it is spherical, it is not going to fail. So this is because of something that is called stress concentration. So it's like poking somebody with a needle versus poking them with a stick, right? Because the needle is so fine, it's going to hurt a lot more. In simple physics terms, the pressure that it is exerting, which pressure is in metallurgy, the analogy to that is stress. So you're able to apply much more pressure or much more stress with the same force. And if you have something which, if you try pressing somebody or something with a ball, you're not going to apply much pressure on them, even if you apply the same force. So it's essentially the same physics that is happening here. These arrangements of carbon, if you can change them, then you can get what we call a spheroidal structure that becomes very soft, very easy to process. You process it, make it into whatever shape you like, and then convert it back into the left-hand side. Because in service, you want something that is hard. So you do something. And there are many other. These are not the only two ways in which we can process and obtain this carbon. There's so many others. But this is just to show you that a simple rearrangement of shapes of the way things are arranged inside a material changes all the properties. And this is responsible for so many industrial shutdowns, so much costly maintenance, so much downtime. So you hear a plant is down for 4 months, 2 months. Often the reason is just something as tiny as this. It's tiny, but it's very difficult to take care of. Could we go next, please? Right. So it's the same principle in daily life. So those of you who've had the unfortunate experience of dropping your smartphones, because now all phones are smartphones, and you lose your screen, and then you either replace it, which is really costly, or you buy a new phone. And you will notice that even the cracks on your screen propagate in a very web-like pattern. So this is where some of the things that we learn from metals apply everywhere in other materials, in non-metallic materials also. Because this is fundamentally related to how, when you drop it, you're putting a lot of energy into it, how that energy spreads around the material. And initially, when smartphones were still new, you do this, and then you lose your smartphone, and then you want to go back to your old Nokia 1100. But of course, mobile phone manufacturers are much smarter. So they said, okay, no, we will provide you with a screen protector, with a screen guard. We'll provide you with Gorilla Glass. So you put a screen protector on it, and then when your phone falls down, it's that which either doesn't break. So that's a very good glass, cordoning glass, toughened glass, tempered glass, so many different names for it. Or it breaks and then it's sacrificial. So you can remove it, right? And that basically follows the exact same principle as carbon and iron. So the way you rearrange them, in case of these Gorilla glasses, these are ions, these are aluminosilicate ions, which change the properties of the glass in exactly the same way that tin changes copper to make bronze, and carbon changes iron to make steel. These ions over here make your normal glass into a Gorilla Glass, which is so tough. Even in that, and this is where it relates to the previous slide, if you see there are two types on the right-hand side on the illustration that we have, two types of crack patterns that can form when glass falls down, right? When this type of glass falls down. So one is a really large crack that can happen, and the other is a number of many small cracks. And I invite you to think about which of these you would like on your phone screen. Now, if you're like most people, you would prefer the one on the left, right? Because the cracks are going to be few. You can still see your screen. You can still go on using it. And that is the basis on which this is designed. But now I'd like to tell you that if that happens, throw away that Gorilla Glass, put a new glass. It should always crack in the other fashion. So the reason is when it breaks in a large manner, first, it's more likely to fail faster. The cracks are going to propagate. So when a crack starts off, it's called the initiation of a crack. And then as it moves across the material, it's called the propagation of a crack. So crack propagation always happens when you have these large structures inside it, like on the left. The whole thing is going to break, and it's also very likely to go down and damage the insides of your phone. So even if it looks better aesthetically, you should stay away from these kind of tempered glasses. These days, you get some very cheap tempered glass on the street, so you can see how they're being made, right? Because this is what the property that you're going to get from those. And you want something like that's on the right-hand side. Yes, it is sacrificial. You can only use it once, but it's going to protect the inside of your phone. So that is a bit of how some of these concepts are applicable even in our daily life. Okay, next slide, please. Right, and this is where we come to a little bit of non-metallurgy, and this is for the other core branches, especially the mechanical and chemical engineers. Since I don't see any mining engineers here, we'll focus on this. So how do we make this rearrangement? We just said it's a simple rearrangement of shapes, and we said vaguely that is something to do with heating. So what is done in such cases is it is heated to a very high temperature, right? And then it is cooled at different rates. Either it is cooled very fast by plunging it into water or oil, or it is treated by just leaving it in air, or you bury it under sand and keep it for a long time, in which it takes a few days to cool. All those give you different properties. But here we're going to talk about the fast cooling method that is called quenching. And this is, again, a word used in common English. And in movies, when you see blacksmiths making swords, they heat it and then they hammer it. So that's essentially forging. And then they plunge it into water or oil or some liquid, right? So that's what cools it. And then they again do some treatment, which is called tempering. So this process, which has again been known from time immemorial, that you heat a metal, especially in something which is made of iron, like you heat some steel and then you put it in water, it becomes very, very hard. So this process is called quenching, and only now we understand it. And now let's move a bit away from the metallurgy and look at what actually happens when you put it in the water. So what you're seeing over here is a tank, which contains your water or whatever liquid you're using to quench, and you're putting that rectangular object inside it. Okay, so remember the object is very, very hot. Typically, it's upwards of 1,000 degrees Celsius. You plunge it inside. Immediately, the water, let's talk about water. The water that's around it immediately becomes water vapor. So that's called the vapor phase. And it makes a kind of film around it. And those of you who remember a bit of heat transfer from school will know that air or gases conduct heat much less effectively than liquids and than solids. So this, in a way, insulates your material, and you want it to cool really fast. That's what's giving you your properties. The moment you had this vapor phase, it's becoming a little difficult for them. After some time, we come to the second thing. So it's called nucleate boiling, right? So if you form the vapor phase, you're not going to get a very hard product. You're going to get a very uneven product that's hardened in certain places and very soft in others. It's definitely going to break the moment you start using it. So in this case, what happens is the water vapor comes up in the form of bubbles. This is what you see when you boil water in your gas stove. It initially starts coming up in the form of bubbles. These bubbles hit that film of vapor that's around it, destroy it, and therefore accelerate the heat transfer, the removal of heat or the cooling of the material. So this is what you always want it to remain in. And finally, it comes to stage of convection, where there's no more any water vapor, it's just water. And convection is basically, convection. It's the movement of fluid because of its temperature. So hot things rise, so hot water rises, and that cooling because of that is much higher than stationary water. So the design of this process requires you to avoid the first, be in the second one for a little while, and then finally come to the third one. And there is years, decades actually, of research that has gone into how you should quench, how long you should quench. And from personal experience, I can tell you that difference of a few seconds in this, of a few degrees Celsius, so difference of a few seconds can make all the difference. You can end up with a part that's going to last you for 20, 30 years, and you can end up with a part that is going to break in the next half an hour. So that's the kind of things that come. And this is where metallurgists often use thumb rules, use what are known as the industrial standards and so on. But this is where the role of heat transfer specialists, which are often chemical engineers and mechanical engineers, come in. So to design a process, you need somebody who really understands this part of things very well. So that is where materials engineers need to interact with the other disciplines. And that's why it's necessary for you to speak the same language. So you have to understand the vocabulary that other engineers use. You cannot say that I'm BTech metallurgy, so I'm not going to talk about heat transfer. I'm not going to talk about Nusselt number or Prandtl number. And likewise, if you're a mechanical engineer, say, I don't know about austenite and martensite. I don't want to know. You don't know is fine. But if you want to work together, and you have to work together because that's the way industry is structured now, you need to find a middle ground. So this is possibly the most important thing that I can tell you. If I were to tell you just one thing, if you take one thing away from this, just be open to people who've had different educations, be open to the way they think about things. Sometimes you may find that thinking about things, stepping into their shoes and thinking about things, clear your own understanding of things very well. Right. So let's go to the next thing after. Yes, this is the practical application. So earlier I showed you images or diagrams of a small tank with putting things, and this is how things actually happen. So even if it's a part as small as a gear, I told you you always like to mass produce, so you won't like to treat one gear at a time. You like to treat thousands or millions of gears. So that bright object that you see in the middle is a huge trough filled with millions of gears. It's being put into a tank. You can just make out that that tank contains water because you can see the reflection of the structure behind it. So that's how red hot it is when it comes out. And to tell you how difficult it is over here, so I took this photo standing at this distance of maybe 20 meters, and from that distance it was unbearable. The heat was unbearable. There was steam all around. The photo was quite blurred because of that. So small changes that I was telling you earlier, that the differences of a few seconds or a few degrees Celsius, which make so much difference, can be very, very difficult to practically implement. And to do that well, you need to cooperate very well. You need to work like the fingers of your hand. You cannot have your thumb moving separately from your index finger. You have to work together, and you have to respect the experience of people who've done this thing. So you may often come across situations where, being an engineer from a prestigious college, you are put in charge of people much older than you, and you've got to manage them, especially in the core engineering branches. And you may often feel that they don't understand what they do, but what they know through experience, even if they don't understand the science of it, is a lot more than what you will learn until you spend enough time in your industry, right? So respect that, and don't think that knowledge is the primary thing. Well, knowledge is primary, but theoretical knowledge is one thing, and learning things practically and experientially is another. And that also is got historical examples, right? Like we saw earlier that sometimes the science comes later, the technology comes first. So it is possible, it's entirely possible. In many industries, you'll see people who don't know any of this, who don't know metallurgy, but who make beautiful products. You tell them what you want and they'll make it, because that's the role of experience and of prior history. And that also tells you why documentation is so important. The moment you do anything, and this should start from when you do your laboratory experiments, anything that you do that is creating knowledge or confirming knowledge, you must document it in such a way that somebody else who reads it is able to understand. And the only people from my experience who do this well to some extent are the computer engineers, because software engineers often write code which at least other software engineers understand. And in my work, I often have to use code written by other people. And I find a huge difference between code that professionals write, or that computer engineers write, and that maybe physicists or other engineers write. So you have to, when you do something, when you're documenting something, you have to remember that you're documenting for somebody who you don't know. So it must be in such a way that they can understand it. If they cannot understand it fully, they know where to look. It should not be something that is very obvious to you, but completely blank for somebody else, right? So that is a bit of learning from these things. Yes, let's go next, please. Okay, so we'll just quickly move through this. This is an interesting story of nickel. So nickel has had a very amusing story. So it was born out of a mix-up. Okay, so metals come from ores, and when you look at a metal, they are quite easily identifiable. Like iron is a gray metal, and when you leave it in air, it becomes brown because of rust, brownish reddish. Copper is a brownish red metal, and gold is yellow. So when you see them that way, they're fairly easy to identify. And the civil engineers, I saw there were a few. This is how you also identify a lot of ores. This is how a lot of geology happens, right? Because there are certain appearances of it. But when it is in the ore form, then it is bound with other elements, and it does not always show these metallic properties, elemental properties very easily. So it so happens that the ore of nickel seemed like the ore of copper. So they mined it, they extracted it, and then they started processing it, and they found that, oh, this is not copper, because copper was very much in demand at that time for utensils, for electricity lines, and so on. This is, now we've come almost to the modern era when electricity is happening, right? So they failed to smelt copper, to extract copper from it. So they called it rascal's copper or devil's copper, because a lot of these developments have happened in deeply religious countries. So anything that is not favorable to you is devilish or the work of the devil and so on. And in a lot of the Scandinavian countries, that is the north, the far north, the cold European countries, the Nick is the name for a devilish spirit or a sprite. So they called it Kupfernickel. This is a German name. Kupfer is copper and nickel is the devil. So it was called devil's copper, right? Because it's copper that is not actually, but it's got something devilish inside it. So it had a very bad rap, a very bad reputation. They shunned it for a century. And it was only now we come to war. And one of you had a question about war also. So it improved the properties of armor steel. By accident, they found that if you drop a little bit of nickel into iron, then you can make very strong armor. And even today, you had these kind of steels. They are called Mar-aging steels. So all your tanks, tanks are alternately called armor in military terminology. So armor is consisting of these type of steels, and they are not very, they're very, very tough. They're very strong. They're not very ductile. You cannot shape them very easily. But if something hits them at a high speed, they're very good to resist it. At this point, I'll just take this question that says, what are your thoughts on war or weaponry being the guiding factor on how we use materials? If the focus was only on improving life, how would that change the usage? Very interesting question. But my thought on this is that probably when all this was happening, war was the way to improve life. We live in very different times when most of us have not lived through a war or seen or experienced war. So it's easy for us to look back and say that things should have been peaceful and things, but possibly that's the only way things were possible back then. Having said that, if we look at a hypothetical situation where there was no war, my suspicion is that there would not be so much materials research, because there is a tendency generally, which is nicely summarized by the phrase, if it ain't broke, don't fix it. So, if something works, let it work. So my feeling is that we probably would not have seen the kind of development in metallurgy or in materials engineering that we have seen today. And this goes back to history also. So the countries which processed metals in the best way, India was one of them. So we were one of the first countries, as you may know, along with Turkey and others, to start using gunpowder. So we needed guns barrels can sustain high temperature, can sustain explosions. That was one. Japan, which is today, incidentally, Japan produces today more steel in volume than India does, which is surprising for such a tiny nation, and we are such a large country. So Japan was always a great country in terms of metallurgy. They continue that. Their industry is very strong. Their specialty or their interest in metallurgy also came from the famous katana, the samurai sword. So that is made from a very, very interesting forging process, and it's called the sword which can cut other swords. So supposedly you can cut through steel with that. It's that strong. It can be sharpened that much. It's that tough. So I think historically there has been a strong influence of war, whether we look at modern history or ancient history, and we can only conjecture. But my feeling is that probably we would not have seen this much materials research. Probably we would still be living with copper and bronze. Okay, so we will come back to this. Okay, can we go on to the next slide, please? Yeah, so now nickel is no longer just an alloying addition for steel like an armor. Now it has its own class of alloys. Okay, incidentally, it's been an hour. Am I overshooting time? If I am, then the organizers could please tell me via chat or something, or how much time.
I think we're good. I think you can.
Okay, thank
go
you,
to the
thank you.
presentation, and
Fine,
then we
thank
can have
you.
a Q&A as well. Yeah.
Okay, fantastic. Thank you. Okay, so nickel is no longer just an addition to steel. A lot of elements that we are primarily additions to steel. So when you think of elements like vanadium, metals like vanadium. So vanadium, incidentally, is very common in automobile steels, and I think it was Volkswagen which first started using it. So that made a big change. So their sales shot up the moment they started using vanadium-based steels. So a lot of elements owe their popularity to steel because they're additions to it. Nickel started off like that, and all the stainless steels, the spoons, the cutlery that you use at home, the medical equipment, the surgical things, a lot of other places also you find stainless steel. Those almost always contain a lot of nickel in them, right? But it's gone beyond that. Now there's a class of alloys called nickel super alloys. Just like a man, Superman, you have alloy and super alloy. And super alloys possess exceptional strength as at high temperatures. They are very oxidation resistant. So that means they don't form oxides and So metals naturally are not very stable. They most of them like to react with the environment, other than what are called precious metals like gold, silver, platinum. And they're precious for that reason, because they retain their luster, their beauty for a long time. Iron, other things generally do not. They do form some oxide, and they do. And the whole principle of stainless steel is that you allow the oxide to form, but it's a kind of oxide which prevents further oxidation. So it like forms a shield around your metal, doesn't waste away entirely. But you look at iron, which is, or a steel which is not stainless, you leave it outside, it will form rust, which is an oxide, and will keep on forming rust. So that will eventually eat away the entire material. So superalloys had that benefit. They have very high oxidation resistance at high temperatures. They have very high wear resistance. Wear is something to do with friction. So like when we were talking about gears, you have two metals rubbing against each other. So that creates a phenomenon called wear. Creep is a special kind of degradation that happens in metals when they're exposed to very high temperatures for very long times. So that happens in situations like when you have power plants, because when you set up a huge power plant, you expect it to run for really long, and there's very high temperatures that it's facing. So you don't want it to, you don't want to keep replacing things every few years. They're generally designed for 20 years upwards. So such places you have a special degradation called creep. So it resists that as well. And this is because of something called ordered phases. So those in the image in the center, when you see a lot of small cubes like blocks, like Lego blocks arranged, or you could think of it as looking at a city from the top, from an aeroplane, right? Those are the tops of buildings. So this is how this material actually naturally arranges itself. And this block-like arrangement is got everything to do with its unique properties. So this is now a very big field of research and development. And there are people today who believe that in some time, all the advanced applications will now be will use nickel rather than steel. And just to give you an example of a real life example of how this happens. So there is, in terms of power plant engineering or the setting up of power plants, what you essentially do is you boil water, produce steam, use steam to run a turbine, and that turbine generates electricity for you. So everything has to do with how much pressure that steam is coming at and what temperature it's coming at. So there are different technologies which exploit that, and these all have to do with what is called the critical point of water. I assume you've all come across critical point somewhere. So the early power plants, which is how a lot of Indian power plants are still today, I'm talking about the coal power plants, are called subcritical power plants. So they operate below the critical point. Then you have critical power plants, supercritical, that's above the critical point. And now people are talking about ultra supercritical. And what we are working on today, India is one of, I think, only 5 or 6 countries in the whole world working on something called the advanced ultra supercritical power plant. So this is something which, if you're interested in these sort of technologies, you must read up on. It's a coal-based thing, but it's going to be a very, very efficient power plant. And power generation is a highly ineffective, inefficient, thermodynamically inefficient produce. So if you input, say, 100 joules of energy, or let's just talk in percentage, only about, in your normal power plants, you get only about 20 or 25% efficiency. So if you're putting a whole lot of energy, only about a fifth of it is being used to generate electricity. The rest of 80% of it is going waste. So obviously, as we talk about greenhouse emissions, as we talk about contamination of the atmosphere, as we talk about coal running out, we need to be more efficient with that coal, right? We need to start getting not 20%, but more. And other countries have gradually moved from subcritical to critical to supercritical and so on. Now because we have the unique thing of a huge pool of trained engineers, which you are soon going to be a part of, and we have the need, right? We need to produce a lot of power. We need to reduce pollution. Those of you who live in Delhi and around areas around that, of course, that's not because of power plants, but you know how bad our air quality is in certain cities. And we also are running out of coal. And human development indices are greatly linked to greenhouse emissions and so on these days. So the only way to do that is either you replace coal as your source of energy, which does not look likely in the immediate future, but that is what we are working towards. That's where other renewable forms of energy, tidal power, wind energy, nuclear energy, solar energy, and all come in. But probably for a long time, that is going to continue to be the main source. So you need to make it very efficient. And the most efficient thing that is theoretically conceivable at the present day is called the advanced ultra supercritical power plants. The reason they can be so efficient is because they use these nickel superalloys, which allows them to operate at much, much higher temperatures than our present power plants. Right? So this is another example of how an advance in materials is pushing your technology to new limits. And this is a matter of pride because we are in a very select group of countries, just like we were when our nuclear program started, who are working on this very advanced technology. We are working on this, and hopefully you will hear good things about this soon. But that is an example of why nickel superalloys are so important. At this point, I will just take one question that I saw about greenhouse. So this is, what is your opinion on sustainable manufacturing and production of materials? They are high power processes, absolutely, which release toxic fumes and greenhouse gases to the environment. How do you see them existing with renewables and tight emission restrictions? So, right. So what I said is one of the ways. So if you make it more efficient, think of it this way: if you're burning something with 20% efficiency, that remaining 80% is going out unburned. So you are producing a lot of particulate matter in the atmosphere. You bump that up to 40%. Now you've already reduced your particulate stuff to 60%. So one primary way is to increase the efficiency so you don't have anything. That has lots of other benefits. But other things also, like instead of releasing them to the atmosphere, can you process them elsewhere? There are a lot of ways that this is being looked into. In the production of steel itself, so steel is produced in, iron is produced in blast furnaces and steel is produced in oxidizing furnaces. And this is now such a mature technology that it finds its way in school textbooks. So I think all of you would have come across a blast furnace in, I suppose, class 10 or somewhere around that. So if something is made into school textbooks, then you know it's a very, very established thing. But today people are challenging that, and people are trying to make that process more efficient from a greenhouse gas emission perspective. So there are things that are going on. And yes, these are high power processes. Yes, they do contribute. But our civilization is built in such a way that without these, we'd probably be in a worse situation than the way we are. So removing this technology is not the answer. The way we need to think is to make it more efficient, to make it more clean. And this is an active area now. I feel it's not as active as it should be. So those of you who are looking to work towards for the environment things, I would definitely suggest that this is something you can look into. It's an area that I see really booming in the next 10 years or so. Okay. Can we go to the next one, please? Fine, fantastic. So we finished the metals and materials part, and now we come to this is higher education opportunities, but really we will talk about job situations and so on. Let me just see if there are any other questions which I should take now. Okay, I think all the other questions we will take at the end. Right, so this is what I'd like you to pay attention to, because this is the part that deals with your future after college and the things that are available, the things that are accessible. And what I will say now could seem a little bit harsh in places, but I'd advise you to take it with a pinch of salt, and then you can make your own assessment on whether it works for you or not, right? So the question is low awareness warping your perspective? For me, it certainly was when I was in your place. Now, I invite you to think whether that's happening with you also. Could we go ahead, please? Right, so this is how it starts. When in class 10, you, I'm talking about like the central boards like CBSE and most of the other boards, you're studying everything, and then you've got to make a choice between generally science and commerce and arts, and then you're pushed into science because people say that's what will give you a good profession. That's where you will have the most money, and smart people go into science supposedly. So you're pushed into that. Then you finish your 12th, and basically you are asked to write the engineering entrance exams or the medical entrance exams. Not much else, right? So from an early stage, this channeling into certain fields that are supposed to be lucrative or are supposed to be good for your future happens. And you're not to blame if you fall into that, because that's all that you've seen at that point, right? So you go along with that. And then that continues. Could we go ahead, please? Yeah, and this is how it happens. And I would really like to know if this has changed now. So please drop comments if you feel that this does not apply to you or you have some other ways. I'd really like to know what the current generation of engineers thinks now. But this is from my personal experience that you're in branch X, whatever that is, and then you essentially have three options in front of you. Generally, some people try to put their feet in all three of them also. So either you want to do higher studies in that branch, or you take up a job, whether or not it's related to that branch, or you go for an MBA and hope for better job opportunities afterwards. So yeah, please do tell me if now some other option has come up, or there's something else that people are doing. Maybe startups are one thing, right? A lot of people probably want to start their own company, which is probably a better thing than these. And now if you want to do higher studies, then either you write your GRE or TOEFL and these exams for countries abroad, or you write GATE. And again, in my batchmates, there was a big divide between these people. So those who are writing GATE generally were not writing GRE and stuff, and those who are writing that were sure they don't want to write this. So this is how things start. You get channelized, you get funneled into something because maybe your seniors have done it and that's what you hear, which is natural because you interact most with your seniors. You feel if everybody's doing it, you should also do it. But the first blunt thing that I would like to tell you is that if your reason for doing something is that most people are doing it, that is probably the wrong reason to do it, right? What you do could be anything. You could have any reason for doing it. It may be a very strange reason, and this is important. It may be wrong, right? Like time may prove you wrong. It may prove that whatever you thought of 2 years back was a bad option, and that's all right. So there was a famous commencement speech when I was in college by Steve Jobs. Probably you've heard of him. So amongst other things, he said you cannot connect the dots looking forward. You can only connect them looking backward. So in hindsight, vision is 2020. You can say, yes, I should have done this, or this was the path to take. While you're making decisions, you cannot know what the future is going to hold. You cannot know what is going to do. Present time, just pre-COVID, nobody knew that life is going to change so much. And so it doesn't matter if what you decide turns not to work out. That is also a great learning experience, right? Failure is the best teacher. But at least you made that choice because of something that you believe in. Something, you have some reason. And I'm not saying everything has to be a passion, everything has to be, it can be completely straightforward. You feel that something is going to be lucrative, it's going to secure you financially, fantastic, go for it. Something is going to quench your thirst for knowledge, fantastic, go for it. If you feel that this is the way in which you can change society, excellent, go for that and give it your best. But don't go for something just because everybody else is doing it. And the pressure is immense, I know that, but try to resist it. And that also conversely doesn't mean that what everybody is doing is necessarily wrong. But there is no right or wrong, it's only what's right or wrong for you. So always keep yourself at the center of decisions. Everybody else matters. Everybody else's opinions matter to a very secondary extent, right? So make your judgments yourself. And the thumb rule that has stayed with me and which has helped me all through is that whenever I feel that I want to do something because others are doing it, it's always turned out to be the wrong choice. So now I'm learning not to do that. And that has held me in good stead. So I would encourage you to make your own assessment. Don't take anybody's, what anybody tells you as gospel, not even what I'm telling you. I'm just giving you some ways in which you can think, assess, critically examine, and then make a choice, right? Fantastic. Let's go next, please. Okay, so this is how many options there actually are. So you do your BTech, BE, MSc, whatever. You can either go into industry, then you can go into R&D. Now I'm talking specific of the Indian situation. I'm sure the other speakers who are working abroad, who are studying abroad in the Samwad series will tell you about how things are elsewhere. So I'm leaving that to them. So you have a number of R&D options. In that you have our biggest group of laboratories that is called the CSIR, Council Consortium for Scientific and Industrial Research. So they're meant to do applied research. They're meant to do research that benefits industry. So right, scientific and industrial. So it's supposed to be geared towards them. You also have the national laboratories, which generally deal with the little more strategic things. There's a primarily space, nuclear, or rather atomic energy and defense. And then you have academic institutions like other things. And after all these also, like if you go to an academic institution, you can later come back to a laboratory. You can go into a faculty position. If you choose to go into R&D, you can then specialize and then try to go into a faculty position. If you're in industry also, there is, though I have not made that arrow, but I do see a lot of people spend a long time in industry and then towards the prime of their career, move into teaching positions or move into equally into R&D organizations. And a lot of people also stay in these organizations for their entire career. So it's actually a much, much more complex web of possibilities in front of you than just the 3-4 options that you may think are there, right? And the best thing is that none of these are dead ends. You can always move from one to the other. And increasingly, it's becoming more and more common. You have a lot of schemes which allow you to move from these. We'll talk about some of them now. Yes, can we go next, please? Okay, so simple Venn diagram. You have primarily, let's say you have industry, and how I'm defining these is industry is something that produces products, right? Academia is something that produces human resource, so it trains people who can later go on and produce products. Something R&D is something which supports industry to produce good products. It might work through the academia, it might work on its own. Okay, so for example, between the R&D, so R&D often large industries like you have in the metallurgical industries, you have Tata Steel, so they have a huge R&D department. So they do the company specific R&D. So that's the connection there. Between industry and academia, you have the CSIR. As I said, they use academic knowledge to apply to industry. Between academia and R&D, you have these slightly advanced technologies like DRDO, the Defense, BRC, the Atomic Research Center, NAL, HAL, aeronautical industries. And the thing that's common to all of them in the center of the Venn diagram is GATE. So it's a good idea to write GATE if you are considering, or if you have any option whatsoever to continue your work in India. I would highly recommend it. And I've always been surprised as to why more people from our college don't write GATE. Again, you can tell me in the comments if that has changed, but if I were to estimate in my batch, there were probably just 15-20% of us who wrote GATE. And from my score, and I know the kind of effort I put into it, I can tell you that 80% of my performance in it was just by sitting in class, right? So, so you don't really need to do much more if you're already in this college. So this is what I was talking in the beginning. Being at NIT already puts you ahead of a lot of things. And GATE is one direct manifestation of that. So I think it makes no sense to not write GATE if you have any thought whatsoever of working in India in a core industry. If your option is completely different, if you want to start something, if you want to otherwise go into finance, if you want to do like something environmental, or you want to do an MBA, that's fine. Then ignore this. But almost anything else, I don't see a route to it without GATE. I mean, at least GATE is the easiest way for you and it's most advantageous for you. So, like I said, 80% was just from sitting in class, and the remaining was just by doing a little more. And when I talk about BRC, then I can tell you that's true. That's been true for the industry also. And I can speak with great conviction for the metallurgy department that what we learn here, the number of things that we learn, the breadth of what we learn is more than what is there in most NITs and the IITs that I've interacted with also. So I've often found myself in situations where I've at least come across something, and just by being in the class, it's familiar to me. And so it's easier for me to pick that up. So don't let go of that advantage, which you already have. You've already put in a lot of work to come to NIT. And I'm guessing if you're, doing the courses well, then you're putting a lot of effort there also. So don't let it go waste, write GATE. And then you can always choose whether or not you want to take that up. So somebody has asked, is it necessary to do a master's if you want to pursue R&D and a private company like Tata Steel? Specifically for Tata Steel, yes, they do take masters or PhD students for the R&D, but they do take undergraduates, that is BTechs, for the regular things that includes the production quality assurance sort of departments. And there are people who get in that way and then move into the R&D. But as a general thumb rule, yes, they do take R&D masters, like senior degree students, right? Masters and PhD. The only industries that don't require, to my knowledge, are the Department of Atomic Energy, DAE, and DRDO, for which you can enter directly after your BTech, which is how I did. So we'll come to that also. Right, can we go next, please? Right, so I don't know if I should really spend much time on this. So, but quickly we'll run through it. So GATE has a number of subjects in it. Focus on, and this is largely again to do with metallurgy. I'm sorry if there may be some differences in the other things, but at least in metallurgy, you focus largely on conceptual questions. And there's also a lot of non-branch related things like your general aptitude. You have engineering maths. This is often an area where people lose out on, because in a lot of branches we don't stay in touch with some of these higher math concepts, vector calculus and differential equations and so on. So if you're doing it, pay some attention to it. Don't need to do a lot of things for that. Your discipline specific questions, of course, and verbal aptitude, that's a small part. But here's the thing, you know that these things normally follow a bell curve kind of distribution. So when you're at the top end, each single mark, each thing makes a big difference, right? So if you're somewhere in the middle of the curve, right, if 1,000 people are writing it and you're like 500 or 550, then a few marks here and there is not going to make much of a difference. But if you're in the top 20 or the top 50, then each thing is going to make a lot of difference in what you get next. And you know this because you've come through such exams to enter NIT. So I would suggest, if you are writing GATE, then aim for that. Don't demean verbal aptitude and such. Just spend a little bit of time on it so that you can do well there also. Hari Krishnan, did you take any additional study materials for GATE? Yeah, I did. So there is no, I don't think there's any GATE coaching, at least for metallurgy. But there are some some bundles of old question papers, like old question papers, 10 years or 15 years question papers. I did have that, and I did do those. It was very useful. And I like I said, I found that I could answer a lot of them without specific preparation. So that is the advantage of being over there and being in a good department. When did I start preparations? If I'm not wrong, GATE was in February or something. I started in the winter holidays, so that is, I think, December. Yeah, December. And but that's the thing. If you're regular to class, you don't need to separately, dedicatedly prepare too much for it. This 1 or 2 months is enough, and enough. So I like did I qualified it, and it enabled me to go wherever. But I didn't. I was nowhere close to topping it and stuff. So if you are aiming for those things, certain institutes, certain PSUs take toppers, certain places like the Indian Institute of Science, ISC. If you want to join the master's program there, which is through GATE, then you do need to be in the top 50 or so. So if you're going for that, if you're aiming for that, then I would suggest spending a little more time. Don't just leave it to the last 2 months. Spend probably your final semester. Just keep doing it, fine-tuning yourself. Because at that point, it's not a lack of knowledge that is putting you ahead. It's just these small things. This one thing that you forgot to prepare for, that one verbal aptitude, that thing that you got wrong, or the one formula that there was a half and then you multiply it 2 instead. Those small things which will help you get into the top bracket. So yes, so that is, if you're like really aiming for those things, then I would say spend your final semester, like you do it along with your project, along with things. It doesn't need separate study time, like you take time off and study for it, not required, but spend a semester. And my personal feeling is that to do well, though not to top, but to do well, about 2 months is more than adequate. Yeah, and my preparation was mostly doing the old question papers. Right, we could go next, please. So in academia, what we spoke about first, you have the IITs, ISC, the NITs also now. NITs are doing amazing research these days. So often they use GATE scores as the qualifying criterion. They generally have additional tests and interviews. So this is the period, we've just finished that period, but because of COVID, all the dates are different. But for the third years and second years who may be here, March to June is the time when you should start looking out for this. Just give me a moment. Yeah, so CSIR, the Council for Scientific and Industrial Research, they have something called ACSIR, the Academy for Scientific and Innovative Research. That is one way to enter it. And they also have research fellowships, which are through NET. I think we'll be talking about that later. This is also something which you can apply for directly out of college. Could we go next, please? Right. So, yeah. You could just quickly read what is on the screen. Fundamentally, you have PhD programs in science and engineering. The advantage of doing engineering is, I think, you can still go into sciences if you feel that engineering is not your thing. You want to pursue physics or chemistry or biophysics or whatever. You have PhD programs both in science and engineering. You also have your integrated MTech PhD. So this is somebody who asked about pursuing R&D. This can be one way. So
it will not give you a job after that, but it will make the process easier, because while you're affiliated to a CSR academy, you will have more opportunities to interact. You will be better in the know of things. You'll know when opportunities are coming out. So this may help to convert it to a job in an R&D company. But this is the CSR lab specifically. Yeah, next please. Okay, so NET, that is for the research fellowship, CSR. You may have heard about the news. This was, I think, 7-8 months back, that they greatly increased the fellowship amount for research students. So now they try to make it very attractive. For the general research students, you have pretty good stipend. I think it's somewhere like 35,000 plus per month, which is incidentally what a lot of starting jobs also are. So they're trying to make it competitive with that. And you had this thing called the Prime Minister's Research Fellowship, PMRF, that has almost doubled the amount. So the government is trying hard to get this huge pool of engineers that we have into nation building, into applied research. Because we had this strange situation where we had a lot of engineers. Companies say engineers are not employable. And I'll probably talk a little bit about why that is so. And we also have a shortage of good researchers. So we're just trying to connect the dots. And all these are routes to encourage more people to enter these fields. So NET, you can give it in any of these 7 branches. We should probably just check and see. There may be some updates. This is not current for this year, but there may be something. But broadly, this is, yeah. Next, please. Okay, so in industry, these are the common PSUs that do take engineers. There was a time when they used to come and recruit people on campus. I don't think that's happening now. So they have your common entrances, mostly through GATE. And there are a number of websites. If you just Google, PSU alerts or PSU jobs in PSU, such things, you'll find a lot of services. You just sign up for them, and each time one of an opening in one of these things comes up, you will get an email. And it'll also tell you the eligibility criterion, the important dates and all that. So don't miss out on knowing those things. A lot of people, myself included, did not know when these things were coming out. And that is, there's no excuse for that, especially now with the internet, with so many personalized alerts that come to your inbox. So sign up for those. You don't know which one of it will be of interest to you when, right? So a number of these things cover most different branches. Yes, we go next, please. R&D, okay. So this is what somebody had asked. Company-specific R&D generally requires 4 to 6 years of experience. So that's if you, say, join an industry as a BTech, as an engineer, and then you work there. After that much experience, you generally have a chance to move into an R&D department, or after your master's or PhD and so on. But this is what I'm talking about, your immediate options. So you always have the opportunity to move laterally from an industry, from a practicing engineering job to an R&D job. And then you have these centralized institutes, that is the Department of Atomic Energy, DAE, which I belong to. So they have the GATE score and the individual exam. I had come to college some months ago to talk about that. Probably some of you were there then. If not, you can either speak to your friends who are there, or else you can email me if you want any information about that, specific information. DRDO also has the test called the SET, Scientist Entrance Test. If I'm not wrong, that's happening this year. You could just check. It doesn't happen every year, but DA recruits every year. Certain offshoots of DRDO, like what is now called BrahMos. So BrahMos is now become a separate organization. They deal with supersonic missile. So they, I've heard, have been visiting some campuses for placement. Have they been coming to NITK also? You just mentioned in the chat. I heard BrahMos had gone to the Northeast somewhere. They recruited some people from there. So probably they could come here. You should check with your placement cell. But by and large, DRDO also takes people through a separate exam. So they don't take through GATE, they have their own exam. DAE has GATE and its own exam. You can choose whichever route you like. Yeah, and we go next. Okay, so these are some useful links. The first one is for the Indian Institute of Sciences. And the reason I'm giving that separately is because they have probably the most number of programs. They have like MTech, they have MTech by research, they have MSc engineering, they have a PhD, integrated PhD, externally registered PhD, a number of things. So just go there. They have a very nice website. You can see all the different options. You can go through that. individual IIT websites, because each one of them has slight differences in them. You should check that out also. OCES.hpni.ac.in. This is for BRC, or generally for the Department of Atomic Energy. This is the route that I followed, and I will tell you about that once I finish the others. CSR.res.in, that is the CSR, and I think they're going to have a massive recruitment in the coming years, so you should definitely look out for that. DRDO has a separate site. It's called RAC. It's a separate organization kind of which does the recruitment for them. So you'll get all the updates there. Similarly, for all the other affiliated laboratories like NAL, National Aeronautical Laboratory, National Physics Laboratory, National Chemistry Laboratory, NML, National Metallurgy Laboratory, and so on, they all have their own admission portals, and you can look for those. So I will talk about the third one, that is OCES. That is what applies to you now. OCES stands for Orientation Course for Engineers and Scientists. It is an entry into the Department of Atomic Energy Laboratories, the most well-known one of which is BRC at Mumbai. Then you have IGCR, Indira Gandhi Centre for Atomic Research at Kalpakkam, where I work. You have the Raja Ramna Center for Advanced Technology at Indore, and you have Variable Energy Cyclotron Center at Kolkata. You have the Nuclear Fuels Complex in Hyderabad, and a number of smaller affiliate laboratories around the country, across the country. So the way this works is you either write GATE or they have their own exam. You write either of them, get a qualifying score. If you qualify, then you're called for an interview. Interview happens at BRC in Mumbai. They pay for your train fare and so on. And if you clear the interview, you're further subject to physical, like health checkups and so on. If you clear all that, you're recruited. Then you are called a trainee scientific officer. We call it TSO. You undergo a 1-year training, right? It's a classroom plus laboratory training based on your branch. And from our college, all the branches except for mining are permitted there. IT people should just check. There's no separate IT entrance, but I think you're allowed to apply through the computer science gate. So probably you have to write GATE in computer science or their own exam. You can please check that. All the other branches have direct. You can directly choose your branch there and enter. Once you enter this, you're subject to a 1-year program, which serves as a first-year MTech, if you like. After you finish this 1 year, you are placed, just like you're placed from college, but in college, it's kind of an optional thing. Like there's a chance if you're not getting placed. In this, there is no chance of that. You will definitely get placed. And no matter where you get placed, your starting salary, your pay band, your all your emoluments and everything will remain the same. But where you get placed and what the job nature, job profile is will differ. All right. So after that placement, you can choose to do a 1-year project for engineers. So if you finish that successfully in 1 year, then you get an MTech degree. So along with your work, you do 1 year and then you get it. If you don't want to do that, or cannot do that, whatever, then you still get a diploma certification for that 1 year that you've done. So that 1 year is essentially an on-job, not an on-job, it's a pre-job training. It's a for-job training. It's classroom. You have a separate hostel in Mumbai. You have, just like it would be in a university, you have exams and everything. And based on your performance in those exams, you have a number of choices of where you want to work. So suppose there are 10 students in your, like suppose you're a mechanical engineer, there are say 20 people. The topper has 20 jobs to choose from. The second guy has 19, and that's how it goes down. So it is a fairly competitive thing once you enter also. But having said that, you definitely have a job. You of course subject to certain performance restrictions, like you must get above 50% and so on. That should not be a problem. And then once you get that, then you are called a scientific officer C, following which you progress with experience and this thing. And the unique thing about the Department of Atomic Energy is that it follows a merit-based promotion scheme rather than a vacancy-based promotion scheme. So, so in most government jobs, you get promoted when somebody senior retires. So the whole chain kind of moves at once. or you get promoted with experience, like after 5 years you will move to the next thing and so on. Here it's not like that. At the end of every year you're assessed. At the end of every few years, if you meet a certain level of performance, you can go for an interview. You do the interview well, you're promoted. So it can, you can have drastic changes in how fast you're promoted based on your performance. So that is one feature which is quite attractive to a lot of young engineers, because there is a perception that a lot of the bureaucratic sort of organizations are very slow, time based, not they don't incentivize merit and so on. So that's not the case here. Here, your career is essentially in your hands. You can make it as good as you want, and if you don't want it, then you continue at the minimum pace that there is, which also is all right. There are some people who like to do that. No, that's also fine, but I would not encourage you to do that. I mean, I would encourage you, wherever you go, try to do the best of your ability. You don't have to be the best, that's not in your control, but do your best. Right. Any tips for cracking VRC interview? I've heard it is one of the toughest to crack. I have also heard this, but I'm not sure how true that is, because I have cleared the VRC interview. I've not cleared a few other interviews. So probably it's just a personal thing, but yes, what is true is that it is one of the longest interviews ever. Typically it goes on for between 1 and 2 hours. Generally the median time is like 1.5 hours. So you can understand that if an interview is so long, there is no place to hide. So they're going to ask you about everything that you've studied. And unlike shorter interviews where there is some element of luck, that they may start asking you something that you know very well, so you answer that well and then make a good impression, get confident, and then just clear it. You may get unlucky wherein they stump you with the first question with something that you don't know. So that element is completely removed here, because whatever order they take, they are going to cover everything. So that is one thing. So it pays to be familiar with everything. And if you are not good at something, you should tell them straight away. Like the moment they come to that, you should tell them you're not comfortable with this. That does not count negatively. So you cannot hide. There is no strategizing that you can do. A lot of people I hear say, give tips for other interviews, like start strong, play the interview, get it to your thing. That's not very possible here, because in such a long time, they will come around to everything. Okay. And so, yeah. So if you're asked a question from a field which you're not comfortable with for whatever reason, tell them that. They may ask you why you're not comfortable. Tell them that, because they also know that people come from very different kinds of colleges. Some things that you study in your college, somebody else may not have heard of. We don't have good faculty in many colleges. So that's fine. All those factors will be taken into account. So if you don't know some field, if you're not comfortable with some field, just tell them straight away. That's okay. Second thing is, the objective is not so much to see if you have the information, if you have the data, or if you even get the right answer. What you try to see more is whether you approach it in a suitable way. Because the Department of Atomic Energy largely is experimental organization, right? So a lot of the things, as opposed to a fundamental study, like in Mumbai, you have the Tata Institute for Fundamental Research, TIFR, or a lot of the pure science departments are like that. So by and large, DAE is a experimental thing. So given a problem, they like to see how you try to crack it. You may be totally wrong, right? The process that you're saying may not give you the answer. It may not lead you to the answer. But if you show that you're able to use what you know to get towards that, then that is more rewarding. So the tip for that is, if you're asked a question and which is not direct, and most questions will be like that, you'll not be asked information questions like define stress or something of that sort. You'll be asked, okay, why is a rubber ball more easy to squeeze than an iron rod? Something, and just shooting things off, right? Probably I will tell you a few kinds of questions, at least for the metallurgist, so that you can understand what kind of things they force you to think towards. So when you're thinking, think aloud. Let them know what you're thinking. They will definitely give you hints. They will try to push you towards the right direction. Be open to that. Sometimes they try to challenge you. They try to confuse you. Don't be too scared by that. Don't be resistant if they're giving you hints also. So basically, you need some presence of mind. And unfortunately, presence of mind comes when you are thorough and comfortable with something, and that does not come if you are just preparing the week before your interview or something. So the longer, I mean, basically, the longer you've spent with the material, right? If you've been regular with your classes and you've done whatever assignments and things, you should be in a good place. And then you do your preparations well. That helps a lot. So think aloud, whatever you're doing. First, start with the things that you think may be useful. Think of how you can apply them to your concept and so on. Try to answer the thing. If they say something, they may ask you a question. Okay, but do you think it would work in this way? Think about what they're asking. Are they trying to give you a hint? If they are, take it. So it's like a cooperative sort of interview, and it's also very comfortable. You're not standing writing at a board and stuff. You are sitting. They keep giving you tea, biscuits, and stuff because it's a long interview, right? You will get tired. If you need to go to the restroom and things, I think that's also permitted. It's a pretty relaxed atmosphere that way. So in that sense, it's not tough. It's not a hostile environment, but it's very, very thorough. Now, about the preparation, I would say don't leave out any topic. Definitely, everybody, when they're in a course, they do have certain things which they are quite comfortable with, which they like more, which they may know better in detail. It's good to have that. They may ask you also, you may start with that. That's fine. But don't leave out things that you don't know. Try to at least be familiar with the basics. So they also, the interviewers also understand that you will not be equally interested in everything. But you cannot let your interest come in the way of not knowing the basics. So there is something very basic that you are expected to know. You should know that much. A little next question, which is probably a little based on application, you don't know, that's all right. But the fundamentals don't leave anything out. Even if that means, going back to your old books, your second year books, your third year notes, whatever, just be familiar with everything. And the things that you really like, the things that you're good at, really specialize in those. It could be anything. Like whatever branch you're in, it doesn't have to be the popular things of your branch. Whatever it is, just do. So, and okay, one most important thing which somebody told me and really worked for me is that probably a week or 10 days before interview, stop preparing, right? Just take a step back, allow everything to synthesize in your mind. You'll start making connections between different concepts. That is what is going to help you in a pressure situation. When you're asked a question which you don't know, at first nothing makes sense, but only if your concepts, you're able to interrelate everything, you will start moving in that direction. Then they'll help you and then you'll move towards it. So in this regard, I will tell you two questions, one from metallurgy and one from mechanical. I'm sorry for the other branch people, but since I don't know what is asked there. But if you want to know that, you can email me at the end. I'm leaving my email ID. I will try to speak to people and get you some, example questions. So starting with mechanical, one question that for some reason stumps a lot of people is that why can't you make puris in water? Right? Why can't you fry puris in water? Why do you need oil to do it? Okay, so it's not necessarily a tough question. If you happen to hit it immediately, you know exactly what it is. If you don't, then you start with the concepts that you have. Okay, what are the differences? What is happening when you're frying the puri? There is heat transfer, yes. How does the heat transfer in water and oil vary? How does that affect the product? What is happening to that ball of flour that is changing? Another thing that they ask a lot is about designing a pressure cooker. So they ask you what is the weight, like if you have, a pressure cooker of certain volume and you're cooking with a certain amount of water, what sort of weight of the whistle would you like to put on it? Because that becomes something that you have to work out, but it includes a lot of things. So you need to know something about the thermodynamics. You need to know something about the material itself, how much heat you are supplying, that sort of thing. So it will start with a very simple question, like how does a pressure cooker work? And then it will go into this sort of thing. And then as you keep, the better you do, the longer, the further they will go until some point when you cannot go, and that's when they'll move on to the next question. So you should aim to be able to answer at least like 1, 2, or 3 levels of those questions, right? So if you are doing that, then you're pretty good. And so happens that you've done that, and one question you could answer all the way till the end, then you're almost through. And one thumb rule is generally if your interview is going on pretty long, then you're doing well. They're happy with you. So that is for the mechanical. Just 2 questions that I have heard from people. So that from metallurgy, of course, I can tell you from my own thing. So what they asked me, one of the things, the interesting things that they asked me was, how do you know that vacancies exist in the material? You've been taught that in class, but why do you believe it? How would you test that it is true? So there's again no one answer to it. There could be like millions of ways in which you try and answer this, but they will. Okay, that's one more thing. If there are millions of ways, then they would like to see if you start with the most fundamental thing about it, right? So in this vacancy case, the most important thing that vacancy has to do with properties. And remember, we're thinking a little experimentally, right? So we have to figure things out and apply it. So experimentally, the vacancies figure a lot in diffusion. Second years, if you're not familiar with this, don't worry, you'll know it soon enough. But diffusion, so you can think of something based on diffusion. Say, okay, fine, vacancies are needed for diffusion, so I will do a diffusion experiment and do this. So that's a way in which you need to approach questions. And all questions will not be like this, but these will be the ones which kind of make or break your interview. You'll always start with some basic, simple, direct questions. If in those very simple questions you goof up, then that can count negatively against you, because that would show that either you have not, you're not paid attention classes, you're not grasped the fundamentals. If you didn't grasp the fundamentals, there's no point in going further. That's the way they do it. But otherwise, they will keep on, going to different questions, different areas. It's also a huge panel. There, at least in metallurgy, when I did it, there were at least 12 people. They kept moving in, now bringing food, snacks, and things. So you shouldn't get intimidated by that. They're not trying to scare you. They're not putting you under pressure to see how you deal under pressure, but they do try to see how you deal with something that's unfamiliar to you. Whereas other interviews may try to deal with how well you know something you've been taught. Here, they will try to gauge if something that you've not heard is in front of you, how you would try and handle it. So that is the thing. And like I said, wide coverage of subjects. So know a little bit of everything. And if you don't know something, be upfront about it. If you're asked why, again, be upfront about that also. And it would not obviously make a good impression if you say, yeah, no, this used to be morning class, so I used to oversleep, be late for it, so I don't know what's happening there. Naturally, that is not going to make a very good impression, right? But on the other hand, if you say that, fine, this thing, we were between teachers and we didn't have whatever, or for whatever reason, this particular concept, I was never very good in maths, so I could not follow this thing too much. Process engineering always was difficult for me. Something of that sort, which is true and reasonable, will be counted in your favor. Right? So they're very accommodative that way. So that is, I think, all I can tell you about the BRC interview. It would have been happening now if not for COVID. Actually, I think it would have happened in June. By this time, people would have been selected and so on. So I don't have information about when it's going to happen, but you'll definitely get to know. And those of you who are doing it this year, who've applied already, you will get updates from via email or whatever. Okay, I think this is my last slide. Could you please see? Could you go to the next slide, please?
It's not going to the other slide. Hold on, just give me a second.
Oh, fine. Okay, in that case,
I think this is it. I think.
Okay, this is it. In that case, could you go to the first slide, please? Because I've dropped my email ID there. So, and if you're interested, if you want to know any of the things which I've discussed over here, again, my request is please don't screenshot. Contact me and then we can share those things with you. While this happens, I will just go through the questions that have already come. If there are any more questions, I'm happy to go through those. Right, Rahul Reddy, I have answered you. Opinion on sustainable manufacturing also we spoke about. How is it determined in the industry that a phase change has occurred in steel? Well, so there are different manifestations of phase change, or as we call it, phase transformation. So essentially, phases are arrangements, are structural arrangements. And properties vary when you vary the structure. So some properties could be, for example, density. Like in this example of when I was talking about hardening steel. So essentially, you're taking it from austenite to martensite. There is an expansion that happens in that process. So you can measure the change in volume because mass is, of course, conserved. So the volume would change. In some cases, it is possible through, say, thermal measurements. The conductivity would change. The electrical resistivity or electrical conductivity would change. A lot of times, we fundamentally go to a microscope. We put it under a microscope and we polish it. That is, we prepare a specimen, treat it with some chemicals. And the way it visibly looks is enough to tell us that a phase has changed. Otherwise, structurally, there is a phenomenon in physics called diffraction, which is essentially the bending of light or an electromagnetic radiation around some object. So if you think of an arrangement of metals as a mesh or as a grate, right? So there you have atoms and you have some space between those atoms. So those grates serve as places through which diffraction can happen. And diffraction gives you a very good idea of what the structure or the makeup of that material is. So this is done through X-rays. A very, very common thing is X-ray diffraction. It's done through electrons, either in a transmission electron microscope. Currently, a very popular technique is called electron backscatter diffraction. So these diffraction techniques are a very good way to understand the change in phase. But often you don't need to go to such techniques, just seeing it under a microscope or the physical changes in the thing like the dimension, sometimes your thermal conductivity, thermophysical properties, electrical properties, these are enough to tell you. Rahul Reddy, how do industries verify infrastructure health at a microscopic level? So often what is done is, suppose you have a component, like on your front screen, you have some large structure and you have a piston which is pushing it through. And you want to know how well your piston is doing because it's moving with a lot of things. So what you'll do is you'll place a basket maybe under it and you'll keep the same metal, a small piece of the same metal. We call it token or a coupon. And time to time, we'll keep taking that out and testing it and seeing how much things have changed. And infrastructure health, especially in the long term, damage is often cumulative, which means that if there is X amount of damage in 10 months and then Y amount of damage in another 10 months, probably you can sum them up in some way, X plus Y amount of damage, right? So there are certain tests that you can do. You take a small piece of the material, you subject it to some load. Like when it was new, you knew how much load it could bear. This load may be in terms of fatigue load or creep load or any kind of different thing. And you take a coupon which has been exposed to the same conditions and you see how much the reduction is. From that, you can estimate how much more life it has, what is the remnant life of it. And yeah, microscopic level, you need to keep some piece separately. Generally, it's not possible to cut out a piece of your component unless it has failed, in which case it does not become health verification, it becomes failure analysis. So that is the thing. As a metallurgist, someone working with practical experimentation, how has lockdown and quarantine affected my research and work? Okay, so it so happened that because we are in a place similar to Surathkal, which is little away from the densely populated cities, we were exposed to COVID a bit late. So we were under a much shorter lockdown than most people were. So we were slightly lucky, and we used to go to office at some, in a staggered manner. Like instead of all of us going, we would go, maybe half of us would go one day and so on. So it wasn't stopped altogether, but to answer the question, how it affected was that a lot of us, we tried to plan our work in such a way that we could finish a certain amount, right? Do certain tests and then take them back home, which you could analyze offline or remotely. So those activities are what people typically do, either analysis of your results or modeling, simulation, these sort of things which don't require laboratory. Probably you can do it with a computer. Those who are engaged in theoretical work, I have been doing a lot of simulation and modeling work in this period. So that was the only way I could use it well. Right. Thinking of startups. Okay, so things haven't changed too much. It's still MBA, higher studies, job, and startup. Okay, Tata Steel, study preparations. Okay, thank you. Thank you so much. I'm so glad you liked it. Any more questions? I'm happy to take them now. Right, and this is my email ID. I hope you've taken it. You can mail me anytime. I will definitely respond within 2 days. And if there is anything about this talk that you would like to know more, or anything about metallurgy, or anything about the institutes, whatever I showed here, anything about the Department of Atomic Energy, we can do that. And if you want to speak to other people from metallurgy, my batchmates, they're all over the world. They're doing very interesting work in different areas. Some of them are working in the automobile sector with very good companies. Some of them are working with very advanced materials. Like I spoke mostly about conventional, traditional metallurgy, metals and alloys. Some people are working on advanced materials like graphene, graphite, energy storage applications, fuel cells, and so on. Some are working on what are called functional materials. There's a wide range of people who are working, who are studying. one of my batchmates is one of your faculty members now. So there are a lot of people who you can reach out to. And okay, one more thing I would encourage all of you is don't miss out on the opportunity to interact with your faculty members, right? Like, I'm sure you all interact with your seniors a lot, and you'll be close to a lot of them. You'll get a lot of inputs from them. That is great, but don't think that can substitute interactions with faculty. So outside the classroom also try to interact with them. It can be because of something you've read, something you want to know more. It could be related to coursework, not coursework, opportunities, their suggestions. From my experience, they've been very, very open to share. And I can credit them that some of the advice they give me, I did follow in terms of choosing a career. Some I didn't. But whatever they told me was golden, right? So it was really good. So do that. Keep in touch with them. And okay, just as a thing, are any of you planning to, or would any of you like to pursue research as a career? You could just drop that in the comments. Maybe we can talk about that a little bit, and those who are not could start disconnecting. Because there are certain things that if you're looking at research, you need to especially think of besides knowing your subject matter well. Okay, so that's one yes here. So in research and in most other things, it's very, very important to communicate, right? And you already hear about communication. You probably have a course on professional communication, group discussions and things like that. That's not what I'm talking about. That is very important. That's your interpersonal thing, your command on language and so on. What I'm talking about is core, hardcore, hard-boiled engineering stuff. It doesn't matter. The language of choice doesn't even matter that much, but what matters is that you're able to communicate a complex idea to somebody else and make them understand, right? So when we were studying and we had to give a lot of seminars and things, there used to be a common phrase amongst all of us saying, if you cannot convince, then confuse. So that works in certain places, but don't make that a life philosophy, right? Your aim should be the opposite of that. You should not confuse it. No matter what complexity of concept or idea you're talking about, the person you're conveying it to should be able to understand it or appreciate it. That is the only way you can progress further. This is true for oral communication. It's very true for written communication. Because when you write a report, when you write an academic paper, when you publish something, you don't have the luxury of explaining to somebody who's not understood. We don't have, this sort of back and forth conversation which you can. So once you've written something, it should be unambiguous. Anybody who reads it should be able to understand. And this does not come necessarily with good command over language. You may be a fantastic poet or a writer, but the ability to communicate complex ideas is slightly different thing. Command over language helps, definitely it does help, but it's more to do with your mental thing, how you structure it in your mind, right? So the more you work on that, and the only way you work on that is by reading complex things, which is books. I would not suggest you read academic papers too much unless that is part of your curriculum, because those tend to be very, very specific, very, very narrowed down. So read books. This is the boring advice that I will give you. Go to the library a lot. You should be like, changing your library books. I don't know how much you can borrow now. We could borrow, I think, 4 books at a time. You should be running through them. You should be exchanging books a month at least. And this is not for doing your exams well. I'm not saying necessarily issue books that are related to your subjects or your course matter. If it's related to your branch stuff, that's good because it'll work for you doubly well. But go after complex things. Try to understand them. That will enhance. It will enhance how you think. It will improve the quality of your mind. But also you will learn how the author has communicated something so abstract in a way that you could understand it. Maybe he's written it 50 years ago, and now you're sitting here, completely different context, different environment, and you're still able to understand that. That's how knowledge grows, right? So the only way you can really improve communication is by engaging with this sort of content a lot. So I would highly, highly recommend. And the library has, I think, always been the most underutilized part of our campus. We have a pretty good library. Do go there. It's fine if you're bored of like metals. You want to read about advanced ceramics. You want to read about photovoltaics. It's fine. And that will also sometimes help you to speak with your faculty members. You read something, go to them, take an appointment with them, go to them, discuss something. That's how you establish rapport. That's how you get a lot of very helpful inputs from them also. So that is one suggestion, especially for the research-oriented people. Even others, it can't hurt, right? The better you communicate in every aspect of life, it's very important. What are your thoughts on doing a PhD after BTech if you're very narrowed down on what you want to research? Well, if you're very narrowed down, and again, I would ask you to be very critical with yourself and to ensure that you do really want to do that. If that is the thing, then go for it. By and large, I happen to ask the very same question to my final year project guide. He told me not to do it because he said, you don't you think you're interested in this, you may not be, and you don't know what kind of guide you will get. Look, what happens is, if you go the stepwise way, right, you do your masters and then you look for PhD, you have a little more time to really experience, to test the waters and see whether that's what you like, and then whether you want to work on it more. Plus you have options. So this is an unfortunate truth. Sometimes it does happen that students and guides don't get along, right? So if you're a master's student, you have a little more flexibility. You can still go somewhere else. After your BTech, if you put all your eggs into one basket, and God forbid, if things should go wrong, then you don't have too many options. So these are the things that my guide and teacher, mentor had told me. Having said that, I have also seen the contrary. I've seen examples of people who've done fantastic well by pursuing something like this. But the thing you should really question is, how do you know that you're so narrowed down in that? Is it because it could just be that that's what you're exposed to, right? Like this is relate more to the metallurgists over here. But my first research internship I did on titanium alloys, and then my final year project, my industrial training I did in an automobile industry with heat treatments, and then my final year project was on polymers with rubber and polythene. And then I started working over here in my present job with shaping metal. So there's no thematic connection between them. All the same parts from those have influenced, and they help me in what I'm doing today. So at that time, if after my first thing I had decided that this is what I want to do, I'd have just gone in that direction. And again, there's no way of knowing whether it's the right thing or wrong thing. But you should just know that this is the possibilities. These are the things. And I would not say don't do it. There are people who've done it well, but just make sure that you know your reasons, right? You have to be very critical and truthful to yourself. And then there are a lot of integrated programs. It's fantastic because you get PhD soon after college. So you'll start a very early PhD, and that can be a big advantage if you're looking at a research career, especially an academic career. That's a great thing. If you're looking at industrial research, then it will not necessarily help you so much. But if you're looking at academic thing, you have a PhD by 25, that's fantastic. Like a lot of people historically who've done great things have finished their PhDs very early. So they say that you're in the prime of your research, like between 25 and 35. You already had your PhD. PhD is research. You've been trained to do research well. So you can do great stuff. So I would suggest be very, very careful. Once you've decided, go for it. And it can be a very good thing. But that's not what I did. And generally, I would not recommend it, but only you can know what is best for you. Right. Thank you. Any more questions? Okay, thank you. I've taken more than 2 hours of yours running into dinner time. Sorry for the initial difficulty with sharing my screen, my presentation, and all that. Thank you so much for being patient. A lot of you stayed right till the end. I really appreciate that. Like I said, it's great to speak to you. Through you speaking to you, we relive our time there, which was, without exaggeration, some of the best time of our lives, right? And you will find that alumni, that seniors are more than happy and willing to help out with whatever they can. So don't hesitate to reach out to any of them. And thanks to social media, thanks to Facebook, it's not difficult to connect with somebody and find out them. People may take a little time to respond sometimes, but that's okay. Just drop them an email, tell them what you want to, or whatever way you contact them, that's fine. I'm sure most people will get back to you, and try to start building a network. Right? You don't know at which point in your career or which point in your life who's useful. So the earlier you start, that's right. Thank you so much. Thank you all for also taking the time, and thank you for the organizers. Thank you to the organizers for arranging this, and good luck. Talks. Thank you.
Thank you so much. Thank you for coming.
Thank you. Thank you so much. Thank you so much.